Hi, everybody. Welcome back to Introductory Physics, day 21. Wow, I can't even believe it. We only have 4 days left, including today, of our class together. And then there is going to be an enrichment opportunity this Friday, I believe. So make sure you check that out as well. But yeah, we are approaching the end of our time here. So if you guys have any questions about anything that we've talked about, feel free to send me an email or ask in the chat if you're watching this live. And I'd be happy to help you out as best as I can. The current plan for this week is to go through chapter 12, gravitation, today and tomorrow. Move on to periodic motion on Wednesday, probably. And then on Thursday, we'll do either some review, if that's what you guys would prefer, or we can go back and talk about rotational motion a little bit more. So let me know what you guys think. If you guys want to do some review problems on Thursday, or if you want to just keep pressing on and doing a new topic, let me know what you prefer, and I'd be happy to do either one. But I suppose we will roll into things today with chapter 12, gravitation. So these are just two quotes that I think are really interesting. I just really like considering things like this. So first one, we live in a changing universe and few things are changing faster than our conception of it. And I just think that's really profound because we think we know all of this stuff. And I mean, we do know a lot of stuff, but there's so much more that we don't know yet. So much more that we don't understand completely. Like, what the heck is dark energy and dark matter? I don't know. So there are still a lot of questions that we have to answer. And we have made leaps and bounds of progress, but we still know hardly anything, which is just incredible to think about. And then the other quote there, pick a flower on Earth and you move the farthest star. I think that's really interesting to consider too, especially for our topic today, which is gravity. So we're going to see why that quote is accurate and not just this like cute metaphorical statement. We'll see that as we go today. So I want to give you, first of all, a little bit of historical context about gravity and how our studies of gravity kind of came about. And especially because I know a good portion of you are planning on studying astronomy, astrophysics, or even aerospace, like some spacey subject at FIT. So I just think it's fun to look into this kind of history of our knowledge. So we're going to start off with Aristotle, who lived more than 2,000 years ago. He lived in BC, so crazy. But he came up with this model of the universe from just really observing the heavens, the sky above. And so yeah, it's really interesting to think about how these earlier scientists made their predictions and their theories and their laws purely just based on observation. And as we go, we'll see how these scientists took previous theories and shaped them, edited them. But really, all Aristotle had to go off of was just observing the sky. Telescopes had not been really invented yet. And they wouldn't be for hundreds of years after this. So all he had to do was look at the night sky and be very, very observant. But from his perspective, here on Earth, it looks like Earth is stationary and everything else in the sky is moving around us. So the sun, the stars, planets, it looks like all of these things are moving across our night sky. And I mean, if you go out and stargaze long enough yourself, that's what it looks like. If you don't know that the Earth is not stationary, it really feels like it is. We don't feel like we're zooming thousands of miles per hour around the sun. We feel stationary. And so he, based on his observations, he created this model of the solar system, really kind of the universe, but the universe in his mind was very small. So this model that he created is called the geocentric model. Geo meaning Earth, centric meaning centered. So the Earth is at the center, and everything else is moving around the Earth in perfectly circular orbits. So the sun, the planets, the stars, all of this moves around the Earth in a perfectly circular, unchanging orbit. And actually, he also had this idea that there were like a fixed ring of stars, like a sphere of stars around us, and that every single star was just kind of at the same distance from us, but in that kind of imaginary sphere. Um, and then that idea of the sphere of the prime mover is really why everything is like moving around us. So that was his model, and the best that he could do based on his observations. A couple hundred years later, along comes Ptolemy, who took Aristotle's model of the universe and kind of edited it a little bit. There are some really weird things that happen with the orbits of Mars, especially, but also um, Venus and Mercury as well, a little bit, um, called retrograde motion. So if you observe Mars long enough in the sky, like if you plot its position every night for a couple months, you'll notice that at the same time, at the same time of night. All right. So it moves across the sky, but then it gets to a point where it appears like it's moving backwards, and then it starts moving forwards again. So it's kind of like, what the heck is happening with that? Retrograde motion, Aristotle's model could not explain that. Because remember, in Aristotle's model, all of the planets were just going in fixed, perfectly circular orbits around the Earth. And so that wouldn't explain why we see these planets go forwards and then backwards and then forwards again. So Ptolemy edited his model with the idea of epicycles, which are smaller circles that planets move around in as they orbit, kind of like, I don't know, like a spirally sort of deal. But each little circle is called an epicycle. And he thought that that would explain the motion of the planets because, I mean, it kind of makes sense, right? As it moves around in circles, um, you would see it moving forwards and then backwards and then forwards and then backwards again. So it seems logical, and that was accepted for hundreds of years. So eventually, along comes Copernicus, who didn't agree with either of those two models, and he created what's called the heliocentric model. Helio meaning sun, so heliocentric means the sun is at the center, and he said that everything is actually orbiting around the sun in perfectly circular orbits. So planets, stars, everything is moving around the sun, and you can see here in his drawing as well. So this little dot right there labeled Terra, that's Earth. And he also said that the moon is actually orbiting around Earth, but everything else is orbiting around the sun. There's Sol, sun right there in the center. Um, and so, of course, up until this point, telescopes still they weren't really a thing. I mean, seafarers, explorers had like spy glasses, but they hadn't really like used them to observe the heavens yet. So they only really knew about the planets up until Saturn. They didn't know about Uranus or Neptune or Pluto or anything like that. That would come later. So this is what his model of the solar system looked like. Sun at the center, perfectly circular orbits, but the moon is going around the Earth as the Earth goes around the sun. And there was a lot of pushback about this particular idea And so it wasn't really widely accepted at first. People still, I mean, they had been believing in this geocentric model of the universe for thousands of years. And so, you know, when you have a very strong opinion about something, something that you've believed to be true your whole life, and suddenly someone says, actually, everything you know is wrong, it's this, people tend to not take too kindly to that. So this model wasn't very widely accepted um, at first. Okay. So Galileo, about 100-ish years later, destroyed the idea of a perfect geocentric universe using his, it says here his invented telescope. Really, he didn't invent the telescope, but he was the first person to tailor a spyglass to be able to accurately observe celestial objects. So in that way, he kind of invented the telescope. Um, he was also the first to theorize that objects are actually pulled towards the center of Earth. So he was the one who theorized about gravity. He used his telescope to observe Jupiter and noticed that it had 4 moons that were orbiting around Jupiter, just like our moon orbits around us. And he also realized that Venus has phases, kind of like the moon has phases. So he made um, actually quite a bit of progress in this field. He also, as you can see in this diagram, he also believed in the heliocentric model. Um, so yeah, go Galileo. Uh, Next up we have Tycho Brahe or Tycho Brahe or however you want to say it. Nobody's like super sure how to say it. I call him Tycho Brahe usually, or Tycho Brahe. That's just what I was taught in high school. But anyway, he was kind of a contemporary of Galileo, and he was actually a super weird, interesting guy. I don't know if you guys know like your famous scientists at all, but he's just funny to me. Um, so he made the most precise celestial observations like ever in this observatory that he built himself. So he created all of these like really intricate contraptions to make really precise measurements of the motions of stars and planets and all that stuff. Um, and it was just incredible. He just so precise measurements, so much. But he absolutely hoarded his data and he refused to share it with anybody. So that's kind of one interesting thing about him. He didn't really analyze his data very much. That wasn't what he was known for. Like Newton coming up, he takes all these observations and puts them together and makes these theories. Brahe didn't really do that. He just took the data, but like the most precise data ever. But then he never shared it with anybody, so that's unfortunate. But anyway, another interesting fact about him is that when he was like in university, he got into a duel with one of his classmates and ended up losing a good chunk of his nose in this duel. But the thing that they were dueling about was who was the better mathematician. That's just silly. But anyway, he lost a big chunk of his nose and he replaced it with a brass nose. So that's one of the things that he's kind of recognizable for. If you see portraits of him or whatever, always look at his nose and you'll know if it's Tycho Brahe or not. He also had an elk that he kept as a pet. That's kind of an interesting thing. And there are a bunch of kind of conspiracy theories about how he died. So one theory is that his nose eventually poisoned him because it was made of brass. And like, why would you stick brass in your body and think that would go well? So that's one idea, is that his nose actually ended up poisoning him. Another theory is that he died from like a bladder infection because so he was like a pretty popular guy. Um, and he got invited to a lot of parties. And back in the day, proper party manners said that you were not allowed to get up from your seat until your host like got up from their seat. And so legend has it that he was at one of these parties, and he had too much to drink, um, but he refused to break manners, and just like get up to go to the bathroom. And so he held it for so long that he either like ruptured his bladder or gave himself a bladder and kidney infection and died from that because he refused to just go pee. So that's kind of an interesting way to go. But there's another theory too, that he might have actually been poisoned or murdered somehow by his apprentice slash assistant, um, who is actually one of our other famous um, scientists that we'll come up and talk about in just a minute. Um, but since he never really shared his data with anybody, he had this scientist working for him for years, just really wanting to analyze his data. But especially, I believe it was like the data on Mars, trying to figure out why Mars has this retrograde motion. And he just would not share it. So his apprentice um, may have killed him to get his data, because then later, a couple of years later, he like published these theories about why Mars has retrograde motion. So that's another interesting conspiracy theory. Um, yeah. So Gabriel, your comment that archaeologists have studied his body and found the cause of death to be obesity, diabetes, and alcoholism. I've also seen articles, though, that say that he died from a bladder infection, and other articles saying that he had like higher traces of toxic chemicals around his nose. So like we don't really know. Um, it's a mystery. Could be a lot of things. Maybe everything just like snowballed at the same time and just took him out. But yeah, super interesting guy. Um, but anyway, using his really detailed observations that he got, he kind of created this, I call it a hybrid um, model of the solar system, because it's not heliocentric, but it's not geocentric. It's like kind of both. Um, so he said that the moon and the sun orbit the Earth, but all the other planets orbit the sun. And so it's like this weird, as you can see from the diagram there, it's just this like weird overlapping circles. It's just bizarre. And then this other idea of the sphere of fixed stars kind of surrounding that out past Saturn. And so this one wasn't really widely accepted just because, you know, scientists tend to have this rule that like the simplest explanation is most likely to be correct. And nature doesn't really have these like super complicated um, patterns. Like usually there's a simpler explanation that is more considered correct. And so since this one is like even more complicated than the previous ones, except for maybe the epicycles one, that one's kind of complicated. Um, People didn't really go with this model for very long. But it is kind of an interesting compromise that he came up with. Anywho, Kepler came next. Kepler was the one who is Brahe's assistant, who inherited slash stole slash murdered his boss for all of his work when he died. And then he used it to create not just 3 super important laws about the motion of planets, but lots of other uh, theories based off of his data as well. So it's like is this something super sketchy that happened here? But like I guess it's a good thing that something super sketchy happened, because progress happened. But anyway, Kepler's model of the solar system is actually the first one that said, maybe circular orbits aren't quite correct. Maybe orbits are a different shape instead. So he said that the orbits of planets around the sun, so kind of a heliocentric model, um, are ellipses or ovals, and not perfect circles. And this actually corrects the problem of retrograde motion, as well as doing away with epicycles. So we'll talk more about his 3 laws of planetary motion later, probably tomorrow. But anyway, this model is the one that is considered correct still today. And actually, the orbits of the planets are fairly close to circular, with the exception of Pluto, which is one of the reasons why it was demoted, if you will. But they're not perfectly circular, and so that's why we see some of these weird things happening. But yeah, this is our model of the solar system that we use today. It's Kepler's model. But still, everything in physics comes back to Sir Isaac Newton, and so he took Galileo's idea of gravity, and kind of ran with it. So usually Isaac Newton is credited with discovering gravity, the whole like apple falling on his head and, oh, gravity, that idea. That's kind of an urban legend. Scientists don't really think that that actually happened. So he didn't actually discover gravity because Galileo did experiments on gravity before him. But what he did discover is that gravity is universal. It doesn't just apply on Earth. Gravity is everywhere in the universe, and it affects everything in the universe. And so he really discovered universal gravitation. He didn't discover gravitation. Kind of a subtle difference there, but an important difference. Let's give credit where credit is due, And so this is kind of what his model looks like, right? Heliocentric, so the sun is at the center there, and then the orbits of the planets going out. He also had this idea of a sphere of fixed stars. That just seems to be a very pervasive thought that is not correct. But I mean, he still rolled with it. Okay. So I guess before we get into that, any questions with this little history lesson real quick? Any questions, comments? Ooh. The thunder scared my dog and my dog scared me. Okay, great. Well, I don't see any questions, so we'll keep on rolling. Okay, the moon is falling with style. So this whole next part of our lesson is based on Isaac Newton's idea of universal gravitation. And so one of the things that he, like one of the leaps that he made in his mind, that whole idea of the apple falling down. But he also said, like, the moon must also be falling. Because if the moon didn't fall, then it would follow a straight line path. So that's of course not what happens, right? We don't see the moon like shooting away from us, never to return again. So it has to be falling towards the earth, just like the apple that falls out of a tree falls towards the earth, because it is attracted to the earth, this idea of gravity. But somehow it falls along a curved path around the earth rather than straight towards the earth. So this is kind of a little picture of what that would look like, right? The moon doesn't just shoot off out into space. It follows this curved path. And so if we remember from a couple weeks ago, projectile motion, when you like throw things, what shape path do they have? What's their trajectory as they fall back down to the ground? Well, it's a curved path, right? It's a parabola. So a nice curve down towards the earth. So imagine for a minute that you're trying to throw a rock around the earth. You're like up on this super tall building and you have this rock and you just throw this rock off this building. Now, if you throw it at a slow speed, then it'll follow that nice parabolic trajectory down towards the ground, just like we would expect it to, and it'll hit the ground in front of the building. If you throw it a little bit faster, then it'll go a little bit farther before it hits the ground, but it'll still follow that curved path as it goes towards the ground. Well, if you throw it really, really fast, then it'll go really, really far before it falls back down to the ground. And it might go, if you throw it at the right speed, it might go fast enough that it'll just miss the edge of the earth. Like it'll fall back down towards the earth, but it'll just miss the edge. And it'll keep falling, but it'll keep missing the edge of the earth and actually just fall around the earth. And that's what we call an orbit, something just falling around the earth at the perfectly right speed. So, you know, if you have a great arm, like a really great arm, then maybe you can throw something into orbit. Usually, though, you need a rocket to do that. So, I mean, that's basically what we do whenever we want to get something into orbit. We just throw it at the right speed so that when it falls back down towards the Earth, it just misses the Earth entirely. And if you throw it even faster than that, then you can kind of control the shape of your orbit, or you can just get it to leave orbit completely, which is called escape velocity. We'll talk about that tomorrow, probably. But that was his whole idea, his whole argument about the moon falling. It's falling towards the earth. It just misses every time. So you can do it, moon. Yeah, but both the rock in that example and the moon would have some velocity sideways, right? You're throwing it sideways off the building. And that would be parallel to the Earth's surface. So that's called tangential velocity. I really like the word tangential. It just feels funny in my mouth when I say it, tangential. But anyway, you need that tangential velocity carrying it sideways. Otherwise, that would be a really bad day, right? So if the tangential velocity decreased to 0, then the moon would just plummet straight towards the Earth. And if the gravitational force were to suddenly become 0, then the moon would just fly straight out into space. Like, I don't know if you've ever taken something on a string and like whirled it over your head and then you let go. It just like flies out in whichever direction it happened to be traveling in when you let go. So, you know, either of those cases is bad news. We need both the tangential velocity and the gravitational force to be kind of in balance with each other in order to keep the moon in orbit. But also, he made the leap to say, like, that doesn't just apply to the moon going around the Earth. That idea is also why planets are in orbit around the sun. We're just falling around the sun and missing every single time. And so we just stay in orbit. So that's kind of an interesting thing to consider. You're falling towards the sun. You're just really bad at aiming / good at aiming because you're not hitting the sun. I don't know. Whatever you think. Yeah. So we just happen to have a good speed around the sun for that. Good tangential velocity. So then, of course, like tying this back to Newton's laws of motion and the whole idea of inertia, how an object in motion tends to stay in motion unless there's an outside force acting on it. Well, he was saying that, um, you know, according to that, the moon going around the Earth would tend to fly out in a straight line, but that's not what's happening. So there must be an unbalanced or an external force that's acting on the moon, that's keeping it from moving in a straight line, keeping it moving in a circle instead. Circle. And so that idea of inertia, remember, is that if an object changes its speed or its direction, if it changes its motion, it was because there was a force that was acting on it. So there has to be some force that's acting on the moon. Thinking too about our talk a few weeks ago about acceleration, there are 3 different kinds of acceleration. Sure, you can speed up, and that's acceleration, but you can also slow down or change direction and have an acceleration. Well, things that are in circular motion are changing their direction constantly, right? They're going this way, then this way, then this way, then this way, then this way. They're constantly changing their direction. So there has to be an acceleration for them. And Newton's second law tells us that if there's an acceleration, then there has to be a net force. So again, thinking about those 2 laws, his first law of inertia and his second law, F equals ma, both of them tell us that there has to be some kind of external force that's acting on the moon to change its motion. And so that force is gravity, the same gravity that was proposed by Galileo, is the same gravity that's holding the moon in orbit around the Earth. It's the same gravity that's holding the Earth in orbit around the sun. It's the same gravity that's holding the sun in orbit around the center of our galaxy, except they didn't really know that yet, but whatever. Yeah, they're both being pulled on by the Earth's gravity. So previously, when we've talked about the force of gravity, we've said that the force of gravity equals mass times the acceleration due to gravity, little g, right? Right. But that's actually only true near the surface of the Earth. And he created his law of universal gravitation that kind of extends this idea to things that are not near the surface of the Earth, like the moon, for example. So this is actually Newton's law of universal gravitation here. This force of gravity equals capital G times m1 times m2 over r squared. That's his law of universal gravitation. That's a really important equation to remember. And especially if you do astrophysics, you'll have that one memorized in no time. Of course, force is a vector, so the direction matters. And the force of gravity pulls things towards the gravitating body. So in our case, towards the center of the Earth. Direction is important because it's a force. So big G is what we call Newton's gravitational constant, or sometimes the universal gravitational constant. Sometimes we'll just call it big G. So big G and little g, they're actually not the same value, right? Little g is approximately 9.8 meters per second squared. Big G is 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. It's a mouthful. And you'll use that number enough times that it'll stick in your brain pretty well as well. But that's our value for big G. And that's a constant. So every time you see it, you'll plug in that same number, just like little g 9.8 is a constant, more or less. M1 and M2 in that equation are the masses of each object. You have to have 2 masses, at least 2 masses, in order to have gravity between the 2 masses. So yeah, you need to have 2 masses, something doing the pulling and something being pulled on. Sometimes we'll use capital M and lowercase m for our different masses. It just kind of depends on what you're feeling what the professor prefers. But anyway, our masses have to be in kilograms. And then R is the distance between the centers of the objects, not between their surfaces. And that's one of the things that students tend to forget a lot, is that it's the distance between their centers, and this distance is measured in meters. Even though it might seem more convenient to use kilometers or astronomical units or something like that, we have to use meters for this particular equation because that's the unit of our gravitational constant, big G. And then thinking about Newton's third law, right, the action-reaction law, there's this idea that, you know, for every action force, there's an equal and opposite reaction force. So thinking about the Earth and the Moon, the Earth is pulling on the Moon, but the Moon is pulling on the Earth with the same magnitude force of gravity, just in the opposite direction. So the gravity on the Moon by the Earth is the same magnitude as the gravity on the Earth by the Moon. It's just the opposite direction. And that's true for any pair of objects that you're talking about, you and the Earth, or the Sun and the Earth. Same magnitude, opposite directions. That's Newton's third law. So it all comes back into play. You know, you never get away from that. And another thing to keep in mind is that the force of gravity is actually a pretty small force. We have 4 like fundamental forces in nature. And compared to some of these other ones, like the strong force that holds atomic nuclei together, the force of gravity is very weak compared to that. Even compared to the electrostatic force, it's very, very weak, which seems crazy because like we're stuck on the Earth, but the force of gravity is actually super weak. And we can only really sense it when we're dealing with huge masses like the mass of the Earth. Even though I am technically gravitationally attracted to my water bottle over here, and I'm gravitationally attracted to my computer right in front of me, and you guys are gravitationally attracted to your cat that's next to you. I don't know your life, you do you. But you're attracted to everything around you gravitationally. So yeah, we can only really sense it when we're dealing with these huge masses. Okay, so I want you to give this question a try real quick. Sedna is 3 times farther from the sun than Eris. Assume Sedna and Eris have the same mass. Compare how much gravitational force each gets from the sun. Okay, so use Newton's law of universal gravitation. Sometimes I call that Newton's fourth law, just because that's faster to say. But use his fourth law there to answer this question. What do you guys think? Well, hopefully you have a guess in mind. Even if you don't feel like sharing it in the chat, that's fine. But we have to remember that this law of universal gravitation is what we call an inverse square law. So it varies directly proportional to mass, but inverse squaredly proportional to the distance. So the distance is a big factor to consider when we're thinking about the force of gravity. And since our distance is 3 times farther, that means we have not just 3 in the bottom, but 3 squared in the bottom. And so A is our correct answer. Sedna has 1/9 the gravity of Eris if it is 3 times farther away than Eris. So this isn't actually a slide, but let's just think about this. What if Sedna is the same distance as Eris, but is 3 times more massive? How does the force of gravity compare in that case? It's the same distance, but 3 times more massive than Eris. How does the force of gravity compare? What do you guys think? Good, Gabriel. Yeah, see if the distance is the same. If Sedna is 3 times more massive, then it would have 3 times the force of gravity if they're at the same distance. So keep that in mind as you use this equation. Yeah, don't get confused as to the effects of mass and distance. Distance is inverse squaredly proportional to the force of gravity, and mass is directly proportional to the force of gravity. Yeah, Casey, that's a good point. Gravity is, it approaches zero, but it will never actually be zero, right? You would have to be an infinite distance away, so r equals infinity, in order to really have like zero force of gravity. But you can't get an infinite distance away from, well, from anything. Especially you can't get an infinite distance away from everything at the same time. So no matter how far away you go from the Earth, you will still experience a very small force of gravity from the Earth, which is what that quote that I mentioned at the beginning, pick a flower on Earth and you move the farthest star. That's why that is actually accurate. You know, there is still a force of gravity between that farthest star and that flower that you just picked. Um, and so, even though it's like a super minuscule force of gravity, it's not zero. So you can never fully escape the Earth's gravity. Um, so, yeah, crazy. Okay. So we've also previously talked about the acceleration due to gravity, and we're going to use that, kind of expand our knowledge on that a little bit. So there is our law of universal gravitation, but we also know that the force of something, the net force on something, equals the mass times its acceleration. Thanks, Newton, again. So that means that if we plug that result in for the force of gravity, then mass times acceleration equals gmm over r squared. And so we can cancel out one of the masses on both sides. It actually doesn't matter which mass you cancel out. So you'll get the same result either way. But our acceleration due to gravity then is gm over r squared. And of course, close to Earth, we say that the acceleration is little g. So little g equals gmm over r squared. But this is our equation for acceleration due to gravity when we're not on the surface of the Earth as well. So yeah, g is our local gravitational acceleration, and which m we cancel out does not actually matter. You'll get the same result. So here's our first real example in dealing with this law of universal gravitation. What is the force of gravity on an astronaut on the International Space Station? The ISS orbits at 405 kilometers above the Earth. The Earth has a radius of 6,371 kilometers and a mass of 5.97 times 10 to the 24 kilograms. Assume that the astronaut is 75 kilograms. There's our value of g, 6.67 times 10 to the negative 11. And how would this force of gravity compare to the values on the surface of Earth? So before we actually go through and calculate this, I want you to make a prediction. Do you expect it to be more or less than 9.8 times his mass of 75 kilograms? You don't have to type that in the chat, but just take a guess, make a prediction for yourself, and we'll see if you are correct. Okay, so there's our astronaut and the International Space Station. And I am going to start off with figuring it out on the surface of Earth. And we can actually do that two different ways. This first way is the way that we've been doing, using the force of gravity equals mass times acceleration due to gravity. So F equals mg. So mass 75, g is 9.8. We get a result of 735 newtons using that method. We can also use our new method, Newton's law of universal gravitation. So gmm over r squared. Capital G we plug in, the mass of the Earth is mass 1, the mass of the astronaut is number 2, and then the distance between them is r squared. So we have to be careful here. One of the big misconceptions, or I guess mistakes, that students make in this kind of problem is assuming that since we're on the surface, the distance between the Earth and the astronaut is 0. And that's not true, because remember, in this equation, r is measured from the center of the objects, so from the center of the Earth. And so r is actually the radius of the Earth there. And I put it in meters as opposed to kilometers, so it's 6.371 times 10 to the 6 meters. And we square that. And we actually get a value that's remarkably close to our approximation. So go us. That's great. But if we forgot to change from kilometers to meters, we would be off by a factor of 1,000,000. So that's kind of a big deal, right? Always check your units in a problem before you just plug numbers in. And then, of course, our acceleration due to gravity on the surface is approximately 9.8 meters per second squared. And remember, that's an approximation. It does vary depending on where you're located on Earth. So if you're at sea level, you are slightly closer to the center of the Earth than if you're up at the top of a mountain. And so our acceleration due to gravity might be slightly larger, than at the top of a mountain. But at the same time, here in Florida, where we're at sea level pretty much, we're surrounded by water, which has a much lower density than a mountain does. And so that would also affect your local acceleration due to gravity. And so like I think I've said before, actually in Melbourne, the Coast Guard measured the acceleration due to gravity here in Melbourne, Florida, and it ended up being 9.792 meters per second squared, because we're so close to so much water as opposed to mountains. But actually, and I thought this was really, really interesting, scientists can use the local measured acceleration due to gravity to figure out if there are minerals or oil deposits under the surface of the Earth, just based on your local acceleration due to gravity, which it makes sense, but it just blew my mind, because of course the closer you are to these heavier, more dense minerals, the higher your acceleration due to gravity would be, because there's more mass concentrated right there. It's just really interesting. Anyway, when we're on the International Space Station, here we have to be careful, because we cannot just put 405 kilometers as our radius. Remember, r is measured from the center of the Earth. So you have the radius of the Earth plus that extra 405 kilometers, which gives us 6,776 kilometers. And then, of course, we need that in meters as opposed to kilometers. So don't forget to do that when you're solving this type of problems. It's not just height above the surface, it's distance from the center of the Earth. So we can plug that distance in to our equation, and we get a force of gravity of now 650 newtons. And the acceleration due to gravity at that point, g, we would use big G times mass divided by the distance squared. So that would be big G times the mass of Earth divided by our total distance from the center squared. And that gives us an acceleration due to gravity of 8.67 meters per second squared, which might surprise people because there is a huge misconception that there's just no gravity in space because astronauts are floating around in the International Space Station, so there must not be any gravity. And that just, it just irks my soul every time somebody says that to me. And I cannot tell you how many of my high school students at Mel High um, believed that. They believed that there was no gravity in space. Listen, if there was no gravity in space, then the Earth would not be in orbit around the sun. We would have flown off into some random direction and be like a frozen ball of ice in the middle of the universe somewhere. Or we would have like hit something or, you know, some other crazy stuff happening. But like, there has to be gravity in space. Like, please remember that. Do me a favor and remember that there is gravity in space. And astronauts are not floating around the International Space Station because there's no gravity or because they're weightless. It's because they are falling at the same speed as their surroundings. Right? Remember, when things are in orbit, they're falling around the Earth and just missing every single time. So the International Space Station is falling around the Earth, and the astronauts inside the International Space Station are falling around the Earth, and they're falling at the same rate. So the astronauts can like bounce around in there and float because they're falling at the same rate. Just the same as like if you are in the unfortunate instance of being in an elevator when the elevator cable snaps, you would be falling at the same rate as the elevator. So you would be weightless in the elevator and be falling and floating around just like astronauts do in the International Space Station. Okay, I'll get off my little soapbox now. There's still gravity in space. Okay. Anyway, this is what gravity looks like for astronauts. So this is measuring from the surface of the Earth. And remember, it's an inverse square law, so the force of gravity varies with like proportional to 1 over r squared. And so this is the shape of what that graph would look like. This is a 1 over r squared kind of graph. So you can see, like, as you get farther and farther away from Earth, the force of gravity that you feel really dramatically decreases, but it's like an asymptote. It never crosses zero. It just approaches zero. So you can never escape Earth's gravity. Anyway, and you might be wondering, like, what's going on with this first part of the graph? Like, what does the gravity look like inside of the Earth? And we'll actually do that in just a moment. But this is the shape of our 1 over r squared graph. So we can combine what we know so far of universal gravitation with things that we learned about previously. So if you did actually get a chance to watch those rotational motion videos, then you should have learned about angular velocity, which is just how fast something is moving in a circular motion. And we give that the symbol omega. Some people call it curly W. It's not a curly W, it's omega, a Greek letter. But that's angular velocity, and that equals the change in our angular position, theta, over the change in time. Kind of like, velocity equals the change in position over change in time. Angular velocity equals the change in angular position over the change in time. Very similar. Centripetal acceleration was also talked about in the videos. So we give that the symbol A sub c for centripetal acceleration. And that is v squared, or your linear velocity, over the distance from the center of your circle, the radius, or radius times omega squared times your angular velocity squared. The period of something So like the period of your orbit is how fast you make one complete orbit. So that would be like the total distance you traveled divided by how fast you did that. That's how long it took. So period, capital T for time, is our total distance, which is the circumference of a circle, so 2 pi r divided by our velocity. And then we just saw this a couple slides ago, our acceleration due to gravity, little g, is big G times m over our radius squared. So we can kind of combine some of these results and get some really interesting, solve some really interesting problems. For example, a geosynchronous orbit. It's kind of redundant to say geosynchronous Earth orbit because geo means Earth. So geosynchronous already means, and like implies Earth. But anyway, a geosynchronous orbit is an orbit that takes like exactly 24 hours to make a complete orbit. So that it stays kind of like hovered over one spot on the Earth. Because it takes the Earth 24 hours to rotate. And so if it takes an object 24 hours to orbit, then those things are synced up with each other. So a geosynchronous orbit is when a satellite is like stationary over one part of the Earth. And we use this a lot for like communication satellites, GPS satellites, those sorts of things are in geosynchronous orbits. But there is a particular distance that those satellites should be at in order to have a geosynchronous orbit. Because if they're too close, then they'll orbit too fast, and if they're too far away, then they'll orbit too slow. So you have to be at that right radius or have the right velocity to stay in that particular orbit. So a 24-hour period is 86,400 seconds. We need it to be in seconds because that's our units for big G. So remember the mass of the Earth is there and the radius of the Earth. What is the direction of the acceleration due to gravity? Well, it's inward towards the center of the circle because the force of gravity is inward towards the center of your circle being the orbit. So that makes the acceleration due to gravity a centripetal acceleration. Centripetal is something that pulls in towards the center. Like if you're swinging something on a rope around your head, the rope is pulling that object in. It's keeping it from flying out. So the rope, the tension in the rope is a centripetal force. So since gravity is pulling it in towards the center of the circle, that would be another centripetal force, meaning that acceleration due to gravity is a centripetal acceleration. The flip side of that, if you didn't get a chance to watch the videos, is centrifugal or centrifugal. I just emphasize it like that because centripetal and centrifugal sound very similar. So centripetal pulls in, centrifugal flings out. So that would be like when you're riding in a car and somebody like turns the corner really fast and you fly out and you like slam into the car door. Or like on a roller coaster, if you turn a corner really fast on a roller coaster, your body like flies outward. That's actually not a real force. Nothing is actually pushing you outward. It's just your body's inertia, right? Your body wants to keep moving in the same direction it was moving, but now your car door happens to be there, so you slam into the car door. Centrifugal is a fake force. It's not real because there's no actual push or pull on you. It's just experienced, but it's really just your inertia. Centripetal is a real force. Anyway, that was in the videos last week. So since gravity is the centripetal force in this case, the force of gravity there, Gmm over r squared, is our centripetal force. So F sub c means centripetal. And according to Newton's second law, the net force equals the mass times acceleration. So a net centripetal force equals mass times centripetal acceleration, which we know from the previous slide, centripetal acceleration is r omega squared. So we have mass times r omega squared. We also know that omega is the change in angular position over the change in time. So since it's making a full orbit, its change in angular position, it makes this 2 pi radian distance. Oh, sorry, that should be 86,400, not 96,400. But it does that in 86,400 seconds. And so we get an angular velocity of 7.269 times 10 to the negative 5 radians per second. And we do want radians in this case as opposed to degrees. It's annoying. Yeah. Anyway, since our force of gravity gmm over r squared equals mr omega squared, we can cancel out, we can cancel out the little m's, and we can rearrange this a little bit to solve for the distance, because that's what we're looking for. We're looking for the radius. So the radius is the cubed root of big G times m divided by omega squared. Big G is 6.67 times 10 to the negative 11. Big M is the mass of our big object, so the Earth in this case. So 5.97 times 10 to the 24. And then divided by omega, which we just found, squared. So that gives us a distance. I did put it back into kilometers. You could leave it in meters too if you want. But it gives us a distance of 42,240-ish kilometers. Again, that's measured from the center of the Earth. So if you subtract like 6,000-ish kilometers, then you can find the height above the surface where we have all of these geosynchronous satellites. But fun fact, when I was looking online last night, as I was like prepping these notes, I discovered that we have, as of yesterday / early this morning, I don't remember, but we have, as of recently, over 21,000 satellites in orbit around the Earth right now. When I checked yesterday, it was 21,006 satellites in orbit around Earth, which is just bonkers. Like, that's so many satellites in orbit around Earth. And they are not all in geosynchronous orbit, because that would just be ridiculous. But yeah, it's just so many satellites, so much, and debris. So like anything in orbit around Earth is considered a satellite. So like debris from other spacecraft is still considered a satellite. But yeah, there's so much stuff. Like, can you imagine though, like the crazy task of having to navigate through that debris cloud whenever you want to send like a probe to Mars or something like that. And it's especially more dangerous when you send people, of course. So like the idea of sending people to Mars, having to fly through all of that huge cloud of debris, it's crazy. Of course, it is like this huge radius, so there is distance between these satellites. But like if you hit one, man, that's bad news. Bad news for your spaceship. Yikes. Are geosynchronous orbits perfectly geostationary? That is the idea of them, yes. And Starlink gonna bump that number way up. Yeah, I don't know details too much about Starlink, but like I do know it's significant. So yeah, it's crazy. So many satellites. Okay. Any other questions, comments, concerns about this example? No? Okay. Moving on. Another interesting thing that we can find now is the mass of the Earth. So the moon's distance is actually going to be really helpful for us. So how can we find the mass of the Earth? Well, we're going to use the moon because we know that they are gravitationally attracted to each other. So the Earth's mass is pulling on the moon's mass, and so we can use what we know about the moon to help us figure out the mass of the Earth. But specifically, we're going to use the distance to the moon. So we know that the moon's orbital period is 27.32 days, um, approximately a month, but not quite a month, which is why it's possible to get like 2 full moons in the same month, which is called a blue moon. Although uh, there's just a bunch of crazy names for interesting moons. But anyway, when 2 full moons happen in the same month, it's called a blue moon. The second one is called a blue moon. But we know that from looking at the moon phases. And so using the moon's distance, we can figure out its angular velocity. So we know it goes around 2 pi radians is 1 complete circle, and it does that in 27.32 days. So I showed there the unit conversion to go from days to seconds, but that gives us an angular velocity of 2.66 times 10 to the negative 6 radians per second, which is omega. The distance to the moon is 385,000 kilometers, and the moon's distance was actually determined back around like 270 BC by Aristarchus. Aristarchus also created a model of the solar system as well, which was heliocentric. He created the first heliocentric model, but nobody accepted it, which is a bummer. But anyway, he determined it using the duration of a lunar eclipse. And then later, Hipparchus, like 100 years later, Hipparchus determined it using a solar eclipse and also using parallax. So if you've never heard of parallax before, you've probably still used it in your everyday life without realizing it. So if you like hold your finger in front of your face like this and then like alternate winking eyes at it, so you close one eye and then close the other eye, you can see your finger kind of like jumps back and forth. It looks like it jumps back and forth when you compare it to a more distance reference point. So like for me, I'm holding it up in line with the word the on my computer screen. And so when I have my right eye open, I can't see the word the. But when I close my right eye and open my left eye, I can't see the word mass because my finger has jumped to the side. So if we can figure out like how far over it appears to have jumped, and we know our distance between our eyes, we can figure out the distance to my finger using parallax, using trigonometry. And so that's what we do actually to figure out the distances to a lot of different objects in space. We use parallax compared to like a background of really distant stars. Yeah, anyway, I think that's super cool that they could figure out the distance to the moon like before telescopes were invented. You know, like it's just crazy. People were so smart. Okay. Anyway, so our acceleration due to gravity is again a centripetal acceleration. So gm over r squared equals r omega squared. So when we want to solve for the mass, if we set gmm over r squared equal to mr omega squared, like we did in the previous example, then our mass is r cubed, right? Because there's an r squared here and an r over here. So r cubed omega squared over g, which means the mass of the Earth is approximately 6.05 times 10 to the 10 to the 24 kilograms. And I mean, you've seen us use this number before, 5.97 times 10 to the 24 kilograms. So this is just slightly off. It's only off by about 1%, which, for doing this over 2,000 years ago, that's pretty impressive to only be off by like less than 1%. Of course, if you work for like NASA or SpaceX or something, you strive to be off by less than 1% because that's still a pretty significant difference when you're like sending rockets places and stuff. But it's a pretty good approximation, which I think is really interesting. Okay. We only have a couple of minutes left. I still had one more interesting question that we can answer with this, but I guess I'll save it for tomorrow because I don't want to run out of time in the middle of that one. But do you guys have any questions, comments, concerns um, about gravitation so far? We do always use radians for angular velocity. Yes. Thanks for answering that question, Marco. Yeah, we always want to use radians for angular things, even though we use degrees for a lot of our angles and stuff so far. Yeah. Any other questions? Eris is a dwarf planet. I don't know if Sedna is considered a dwarf planet. I know there are 5. Oh man, I'm a little rusty on them. Pluto, of course, is a dwarf planet. Eris. Um, they are all out of my head. They're 2 like Hawaiianish sounding names, I think. Yeah, I don't remember. I'm sorry. I'm a little rusty. If anybody else knows what the dwarf planets are. Do I know where they came from? No, I don't remember where the names Eris and Sedna came from. Um, I'm sure they're significant in some way, but I don't remember. Any other questions about the material for today? All right. Well, I hope you guys have a great rest of your day. I will see you tomorrow. Bye.